Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Mike Jordan. I suppose Mike doesn't really need an introduction. Let me just tell you an interesting story about Mike. In 1993, I think it was, I was part of a summer course on graphical models, a one-week course. Mike was a student at that course. And then about a year and a half later, he presented his first paper on variational methods in graphical models, and I think you all know about that work and subsequent work he's done. So Mike is a fast learner. And,
you're a good teacher.
So Mike, take it away.
Thank you. Okay, it's a pleasure to be here. It's a good audience for me. So I'm going to be Bayesian today, but non-parametric Bayesian. And at least the world of statistical machine learning has been either non-parametric or Bayesian. And there's been a big distinction between those two worlds. So all the work on kernel machines that you've heard about and all over the years has been mainly non-parametric and mainly non-Bayesian, although Gaussian processes are an example of non-parametric Bayes. But Gaussian processes are just a little tiny sliver of the world of non-parametric Bayes. And so what I want to do in this talk is open up some of the rest of the toolbox of non-parametric Bayes. It's a small set of people in statistics who work on this topic, but I think it's clearly growing and clearly of interest to machine learning. So let me acknowledge my collaborators. There are several others. Maybe I'll acknowledge along the way, but the main ones have been David Blei and Whye working with me at Berkeley. We're going to be Bayesian today, and we're going to use graphical models as our notation. So I think I'll just leave that slide up for a second just so everybody's clear on, I guess this is entirely standard notation. So we have a graph, and I'm going to mainly work with the directed graphs today. And I'm going to use the plate notation for representing exchangeability. So if I have variables x1 through xn which are exchangeable, i.e. if I can reorder them and I still get the same joint distribution, then Di-Finetti's theorem said that there must exist an underlying theta and with a measure on theta such that the joint probability of x1 through xn is represented in this way. So this is the same as this. You have a probability of theta and then a product of xi given theta. Integrate out theta, that's the representation of x1, probability of x1 through xn, okay? So I'm sure everyone has seen that before, but I hope this is clear. So I have n replicates of xi, and it looks just like that. And so what do you do with graphical models? Well, you condition and you marginalize over variables, nuisance variables that you don't care about, and try to calculate things like posterior probabilities or other kind of or marginal probabilities. And there's a long litany now of algorithms for doing this. There's the symbolic style algorithms that really just manipulate the graph. There are sampling algorithms, and then there are variational algorithms that turn the problem into an optimization problem and perturb the optimization problem and try to solve the perturbed optimization problem. But that's not going to be the topic of the day. This is all background. I assume that all of you know about all those things, and as I'm going through what I'm talking about, whichever of these you prefer, that's what you're supposed to think about. Now, most work on graphical models has been parametric. So each of these distributions associated with the edges are parameterized by some parameter, and this is usually finite dimensional. So if this were allowed to be this could be non-parametric if this is for all distributions, but it's generally not. And in particular, almost all examples out there are taken from the exponential family. Okay, so Gaussian, multinomial, Poisson, Dirichlet, etc., are all widely used. And even within that framework, if you have nuisance variables that are instances of these things, after you integrate over them, things become complicated and unwieldy. And so this already has given a lot of research problems to work on. But what I want to do today is to move beyond the exponential family. I want to be able to allow distributions which are non-parametric, i.e. they have a growing number of parameters, or a potentially infinite number of parameters. That's what we mean by non-parametric. And I want to give you reasons for why we should be doing this, not just because it hasn't been done very much. So let me start by referring to a classical parametric model that I've worked on with my colleagues. and show why this leads to a really interesting problem that you might think of as a model selection problem, but I'm going to argue is really better thought of as a nonparametric estimation problem. So this is a model for text. We have a bunch of documents, and each document is a list of words. And we're going to use a so-called bag of words model, but I hope that in this audience you all realize that that means exchangeable. And really the right word to use is not bag of words. You use the word exchangeable. Because a lot of times you'll see people saying, well, we did a bag of words model, and that's the same as IID, blah, blah, blah. And they make, all that blah, blah, blah is completely wrong. Because exchangeable means, as we saw on a previous slide, conditionally IID. It means conditional on some underlying latent variable, you have IID. And that's very different. If I learn about a first word, x1, that tells me something about theta, which tells me something about x2. And so they are definitely not independent. And so that's very important. Even though bag of words sounds like a stupid model, when you think about it as exchangeable, it's obviously not as stupid as it sounds. Anyway, I think as you all know, the bag of words models are widely used. And this is an example of a probabilistic bag of words model, i.e. we use exchangeability pretty seriously. So here are the words. This is one document here. And so this is document D, and there are n words in that document. Those are the multinomial variables for those words. And each word comes from a topic. Each word can, in principle, come from a different topic, but there are only a few number of topics typically. So typically, for a given document, a lot of the words come from the same topic. But you can have several topics being used per topic or allocated in our terminology. So a document, that's the outermost plate. There are capital D documents in our corpus, so this is a model of a corpus. And the way that works is that you first of all, to generate a new document, choose a probability distribution theta on topics. So Z is a multinomial, so there are k of those. And this is a k-dimensional vector that sums to 1. So these are probabilities of topics. All right, so I might generate a new document that's going to be 0.9 sports and 0.1 travel. And now I repeatedly pick the sports topic a lot of times and generate words from the sports topic, and occasionally pick the travel one, and I get a mixture of the two kinds of words. But this can be any distribution. I could get a mixture on all the topics in my set of topics and generate a new document that's a mixture of all those words. Okay, so hopefully that's clear. And these are hyperparameters. This is just the, we're going to put a distribution on theta. So where do the thetas come from? Well, they come from, in this example, a Dirichlet distribution. So these are the hyperparameters associated with the centering and scaling the Dirichlet distribution. And then these are just the parameters associated with the topics. For each of the k topics, you have a list of the probabilities of the words, and that's what the betas are. Okay, any questions about that model? So what we're going to try to do is move beyond that model. That's a parametric model, and I want the step to nonparametric is a little bit complicated here, so I want you to be clear on that model. This is a more pictorial version of this. So to generate here's a brand new document. We first of all choose a distribution on topics. Say there are 4 topics in our world, and we mostly are using this topic, a little bit this, and not at all this. And so you repeatedly choose a word by choosing a topic, a specific topic from your distribution, and then generating a specific word. And that gives you a distribution on that document. And you do this now for multiple documents. All right, so just to remind you, I assume all you know what a Dirichlet distribution is, but this could be a pretty critical part of my talk, so I want to make sure it's really clear. So there's the density of the Dirichlet with respect to the simplex. All right, so the thetas live on a simplex. They sum to 1, and they're positive. And the alphas are hyperparameters, and roughly speaking, the alpha tells you where the mean is. So alpha divided by the sum of the alphas is exactly the mean. And so as I move those alphas around, I move this thing around, and then the magnitude of the alphas tells me about the sharpness. As alpha gets larger, this scheme gets more and more sharp. So think of it as something like the Gaussian on the simplex, although that's not quite right, because it actually, when alpha is smaller than 1, it goes the other way. You get mass at the corners. Okay, so that's the classical Dirichlet distribution. And now we can explain the LDA model in more geometric terms. I think this is a very helpful diagram. So imagine there are 3 words in your vocabulary, and those are the corners of this simplex. All right, and so a point inside this simplex is a probability distribution on words. So that's what a topic is for us. A topic is just a distribution on words. And so here's a topic. It's just a point in that simplex. All right, here's another topic. It's a different point in the simplex. And now here's a third topic, and so on. You could have more topics if you wish. Okay? So the topics are distributions on words. They're points in a simplex. Now what's a document? Well, in our model, a document is a distribution on topics. Okay, so what's a distribution on topics? That's a point inside this simplex. Okay, so all these dots here, those are documents. All right, and so all our model is doing is saying that by exchangeability, we must have an underlying variable that is giving us that distribution, and we choose that distribution to be a Dirichlet in this specific model. So the rest of the model is sort of, once you've said exchangeable, you don't have much choice, and you want to have topics. That model is just, you have to use that model. But now at this point, we have a degree of freedom, which is what distribution do we use on documents? And so we did the simplest possible thing. We put a Dirichlet here. And interesting generalizations of this would be to allow things like mixtures of Dirichlets or other things in this space. And those are kind of tweaks on the basic LDA model. The so-called PLSA model by Thomas Hoffman, which inspired us to do this work, is the completely non-parametric model in which this distribution is just given by spikes at these specific documents. All right, and so the problem with that model is that you have one spike per document, and that's too many parameters. Every new document has got now k new parameters. So you have n times k parameters. That's way too over-parameterized. So there's all kinds of folding in and tempering heuristics which are needed to use that model in practice. Another problem is that when a new document comes in, and maybe it sits right here, it has zero probability because it's not at any of the spikes. All right, so that model is a little bit broken, and this is one way to fix it. So this is not about the LDA model, but just to give you an idea, these are some corpora that we tested it on. These are perplexities, so you want to be small as a function of number of topics. And these are some of the standard kind of IR models, a unigram, mixtures of unigrams, LDA, and then this heuristic folded in version of the PLSI model. So here's the PLSI and here's the LDA. So it's way better in terms of perplexity on most of the data sets we've looked at. Here's another data set. Here's a recent paper, just published this past few months this month in CVPR by Whye and Perona. So they applied LDA to a vision problem. So they had a bunch of categories of scenes: forest, coast, mountain, country, etc. And for each category, they had an LDA model. Okay, so categories assumed to be known. They had a human label the scenes. And so conditional on that, they had now an LDA model, one for each category of scene. Okay? And I won't get into all the details. The words for them were vector quantized regions of the image, and they made certain choices about how to do that, and so on. And these are distributions over their topics, and these are specific instances of topic distributions. They're kind of interesting to look at. I think the next slide was a specific example. So this is the forest category. These are all they call them, instead of topics, themes. And these are the probability distributions on topics for forests. And the high ones are these here. And I think they took, 20, 19, 3, and 21, the highest probability topics, and gave you the distribution on the words for those topics. So there's a very concrete example of an LDA model fit to some data. All right. Now, before I get to this next slide, they have one of these LDA models for each kind of scene. And so in some sense, that's not a very satisfying thing to do because these scenes are related to each other. And you don't want to have them be treated separately. All right, so you really would like to have a kind of sharing of strength among all these models. You want like a hierarchical Bayesian model. All right, and that's what we're going to be trying to do later in this talk, is to develop hierarchical Bayesian models in this framework. And we're going to see that that's challenging to do. But just the basic LDA model requires kind of a hierarchicalization. Each document is like a separate mixture model. All right? And if you're going to try to go hierarchical, you're going to have to treat the fact that the documents are separate kind of clustering problems, and they've got to be, even just to use one LDA model, you have to have a kind of a notion of sharing. And in this application, you had multiple LDA models. You have kind of a double hierarchy. You have to go up 2 levels in a hierarchy. Anyway, that'll hopefully become more clear later. Just very briefly, this is another application of this, just for the applied people in the audience. That's probably less well known because this is Dave Blei and me. We published this in SIG-IR. I think for the vision people don't pay any attention to SIG-IR, so this kind of escaped their attention, I think. So I just want to briefly mention it. So this is just the annotated data problem. In the Corel database in particular, you have instances of images and accompanying text that a human labeled, and you'd like to learn the relationship between those. So you segment the image in some way, and you turn that into bags of regions, which is what like the Perona, the Lee and Perona model does. The bag of words model for images. We use real valued feature vectors for these things. And now we're going to extend the LDA model to a pair of LDA models that are in correspondence. And so the way that works is you choose a distribution on topics that are image topics. And then each image topic generates a patch of the image. And after having done that choice, generatively then from those topics, you generate text. Okay? And so graphically it looks like this. You have an LDA model for the image, which is up here. It has its topics and its patches and hyperparameters. These are now Gaussian because it was real value data. And then a distribution on that. And then conditional on those topics, you choose from the words using the same topics to index into. So that topic is kind of enforces a correspondence between patches and words. And this is just a uniform variable to say which particular word comes from which. Just a permutation variable. It says which word comes from which topic. So this model works well, and it's better than the previous generation of word and image models, which were just Cartesian products of underlying models. So I had a mixture model for the text, a mixture model for the images, and I took the Cartesian product. That's kind of the standard model that's been out there. And we tried that first with LDA. We did a Cartesian product of LDAs. And that worked just like the previous generation, not much better. But this works a whole lot better. And the reason is because of this edge right here. Without that, you just have a kind of a Cartesian product. You would have another arrow here. And this forces this correspondence. So this topic really becomes a topic that tries to generate both an image segment and a corresponding word. And that brings the data into register. So here's just an example of some images from the Corel data set and their accompanying captions. So humans did this. So there's just a few words for each of the images that are most characteristic. And they didn't say things like blue sky, because it's obvious, right? And so in some sense, the algorithm should help you there. It should be able to tell you whether there's blue sky there as well. So here's some examples, some images from the test set after we fit all of our parameters. And we now condition on those blobs and try to calculate the posterior probability of the words, just using the inference algorithms that these graphical models have. And so here are predictions. And you can just sort of look at those for a minute. You can see that it does pretty well. These are just randomly chosen test images. So it's not solving the hard vision problem in some sense. It's not a relational model in any way. But as a bag of words model, it's pretty impressive. I think, for example, this one here, people in market was actually the human labeled, and then it added these things, which are quite reasonable words. You can also go the other direction. Suppose you want to go in the retrieval direction. Here's a set of words. Give me an image that corresponds to that set of words. That's just a different conditioning direction in the model. And you can do that. And here's some examples. If you type in candy, it gives you those images. If you type in sunset, the ones in the middle. And then people and fish, that's an interesting one. There were very few captions that actually had the two words people and fish, but it doesn't care about that. It's just a bag of words model. It finds images that have high probability under those words. OK, so let me now pause yet again and make sure that everybody's with me before we move on to the harder, more interesting problems. Yeah. Yeah. Yeah, there's a bunch of things in this spirit. And I tend to prefer this one because it's fully probabilistic. We didn't have to do any kind of choices. We just wrote this model down and gave it over to the Bayesian machinery, and that's the results you see. Yeah. Yeah, so there's a lot of things that are similar to this. I'm not saying this is sort of the best or the only or whatever. It's just I was just showing you a modular sort of, we did the LDA and it was easy to do this sort of thing. At the period we did this, the main issue that for a lot of people were looking at was mixture models were not good because you had to pick one topic per image or one topic per document, kind of a clustering model. And all of these models, including LDA, moved beyond that, and Rich Zimmel's thing moved beyond that to say, okay, you can have multiple topics per image, multiple topics per document. And so this is just our particular take on how to do that. But I think the link to exchangeability is pretty important. Once you say the word exchangeable, i.e. instead of bag of words, you're led to a model that's very close to this. And Rich is the way I think about it is I reinterpret it in this language, and I think this is a more direct way to get those ideas out. Okay. Okay, so let's now turn to what I wanted to really talk about, which is the model selection problem. So, as we'll talk about here pretty quickly, one of the model selection problems in general in mixture models is how to choose the number of topics. And a lot of people have worked on that from a lot of points of view. It's usually viewed as a fairly hard problem. There are some, you can do MCMC and so on and so forth, but it's not really a resolved problem. And so I'm going to tell you about the Dirichlet process approach, which I'm sure some of you know about, but probably not enough of you know about it. And we're going to then move to the real part of the talk, which is not how to just do one mixture model problem, but as you're seeing in all of these examples, we have multiple mixture model problems. And how do you choose the number of topics, quote unquote? What do you mean by the number of topics when you have multiple mixture model problems that are linked in some sense? That's our problem. So more generally, how do you choose graphical structure? And there's all of these model selection methods out there. And the problem with a lot of these is they're derived under various assumptions that aren't really very appropriate for the case where you have large amounts of uncertainty about your structure. Either they're kind of based on hypothesis testing kind of framework where you have a null and then you try to say whether something is different from the null, or they're based on binary comparisons of nested models. And some of these aren't based on those kind of assumptions, but a lot of the model selection things are based on things that work well if you have a small number of models that are close to the truth somehow. And that's not the setting in many of the applications that we have in mind here. So another approach to go is just to sort of say, forget trying to be kind of, model-oriented, but just treat this as these models as coming out of a nonparametric model, which can grow in complexity as the data arrive. So let's go back to the mixture models and try to be a little more formal. So here's your classical mixture model. The ith data point is given as a sum over k components of the probability of the component times the density of the data point xi given that component. And the standard way to think about this is you introduce an explicit variable zi. It can be one of k capital K states. It's a multinomial variable. And so conditional on that, you get a distribution f of theta k. So that's the picture. Here's the graphical model where we pick the categories with a distribution pi. And having picked that, we get our xi with probability conditional on z. Okay. All right, and so here's the a non-parametric Bayesian way to try to address this problem of what if you don't know k? Okay, and so again, hopefully you've seen things like the BIC score or whatever. You could try all possible values of k and calculate their penalized score of some kind and then compare them. But I'm going to argue that's sort of not the spirit of lots of mixture model problems. All right, so here's something called the Chinese restaurant process. This was studied in the late 60s, early 70s by probabilists. Mainly trying to make links between combinatorics and probability theory. And so forget everything I've been saying so far, and let's just think about this kind of metaphor. We have a Chinese restaurant in which there are all these round tables, and customers come in one after another. So the first customer arrives and deterministically sits at table 1. There's the first customer. And the second customer comes in and with probability a half joins that person. So here's customer 2. Or with probability a half starts a new table. So it could have gone here. And the general rule is that you sit at a table proportional to the number of people already at the table. Okay? And so, there's a rich get richer kind of phenomenon. If you start to get a lot of people at a table, more and more people want to join into that table. But there's always a probability of starting up a new table. All right? So that's the Chinese restaurant process. And instead of having it be a half, you allow yourself to have a parameter alpha, which is the probability of starting up the new table. And you can prove a bunch of things about this. First of all, this is exchangeable distribution on partitions. So after n people have come in, here's, I guess, what was that, like 8 or 9 have come in, there's now a partition. All right? And if I did it again, I'd get a different partition. And if I look at the partitions, it turns out that this thing is exchangeable on the partitions. I could reorder them and I still get the same distribution. So even though we did this in a particular ordering of people coming in one after another, it turns out it's independent of ordering. Okay, so this is an exchangeable distribution on partitions. You can also prove that after n people have come in, there are on order log n tables occupied. And there's a tail on this, but roughly log n. So it grows as a function of n. That's non-parametric. But it grows sort of slowly. There's a long tail on this thing. I learned about this because I was interested in a problem in combinatorics, which is If I take the integers 1 through n, and you take a permutation of the integers, and you now consider taking a random permutation with equal probability for all the permutations, you can now ask the question, what's the probability that integer I and integer j are in the same cycle? Okay, right? I hope all you know that a permutation is equivalent to the sums of the cycles of the permutation, right? I go along, I look at the permutation, I look where a point goes, and I go around until I bite my own tail. I have a cycle, and I do it again, and so you can ask, what's the probability that integer I and integer j are in the same cycle of a permutation or a random choice of permutations? And you can do that calculation, and so I'd given this as an exercise to students in a class I was teaching, and it just seemed like a nice little exercise in combinatorics and probability, and it's about 3 pages of just writing down formulae and moving things around and all. But the answer you come out with is kind of striking. So does anybody have an idea what the answer is? It's probably that I and j are in the same cycle. Any good guesses? So maybe one fact that's helpful is that there are roughly log n cycles, right? That's a classical fact in combinatorics. There are log n cycles in a random permutation. All right, so that makes it sort of sound like 1 over log n would be kind of an answer. But some will be bigger. In other words, maybe it's not quite 1 over n, maybe 1 over n log n or something. Anyway, the answer, it turns out it doesn't scale with n at all. It's a half, no matter it's independent of n. All right? And that's a surprise. So after you do a long calculation, you get an answer like that. You sort of think, what's going on here? So I went and talked to Jim Pittman, who's a probabilist, who said that I needed to learn about the Chinese restaurant process, and this would all be very clear. And so I did, and here's the proof, which is that Chinese restaurant process is exchangeable, right? It gives you exchangeable distribution on partitions of the integers. So the probability that I and j are together in a cycle is the same as the probability that 1 and 2 are together, right? Because it's independent of ordering. So what's the probability that 1 and 2 are together? Well, 1 sat at this table deterministically, and then 2 joined him with probability of half. So end of proof. And there's about 20 other facts you can prove about interesting relationships in combinatorics and probability using this Chinese restaurant setup. In fact, why do you use round tables? Because that's the cycles of a permutation. And you actually can have other generalizations of this where people sit at various points in here, depending on various other aspects of the process. So anyway, probability aside, this has been used by Bayesian statisticians to give you priors on mixture models. And so I hope that it's already clear. What we've done is to define a prior on clusterings. And so now if you're going to be Bayesian, you will add a prior on parameters to the story. So the first time a guy sat down at this table, he generated from a prior distribution on theta, a specific theta, and that got associated with the table. And everybody else who joins that table inherits that specific parameter value. And if you start up a new table, you get to choose from the prior the specific value theta for that table. All right, so if this is Gaussian mixtures, then when I sat down at that table, I picked a mean and a covariance matrix from some prior, and that became a cluster, right? It has a certain mean and covariance. And someone who started a new table will start up a new cluster. All right, so these are just clusters. And now we have a prior on everything. We have a prior on clusterings, i.e. partitions, and we have a prior on parameters over the clusters. And we get a likelihood just by saying that, using the Gaussian likelihood in this case. The probability of a data point is just a function of the table you're at and the parameters at that table. So we have now a perfectly well-defined Bayesian problem, and we can get a posterior. And the posterior will now be on all those entities. It'll be on the parameters and on the number of clusters. Sure, of course. Yeah, you're a Bayesian, you have hyperparameters. So alpha is the key hyperparameter here. And well, that's the usual issue in Bayesian statistics. You have to set hyperparameters. But the point is that by going up a level in the hierarchy, it's easier to set alpha than it is to set k. And in fact, results, you can find many problems in which you can have alpha between 1 and 100, and it doesn't matter. You get the same answers. Well, you can do, it's the usual story. You can do empirical Bayes. You can infer alpha as the maximal marginal likelihood value of alpha, or you can put a distribution on alpha, and a standard thing to do is put a gamma there, an improper gamma, or a sort of a rough gamma, and you will get out an answer that's a little more Bayesian. And this is widely done, of course, but then you have to check afterwards and make sure that it didn't really, matter so much what you did there to the actual data analysis.
So our imaging particular way of setting up your hyperparameter will be equivalent to some weight in AIC.
No, I mean AIC is very different perspective, and we can get into that later. But let's not get it kind of so. Let's just follow this story for a little while, okay, and see where we go. Okay, so how do you get that posterior distribution? The standard thing to do is to sample. And it took people about 20 years to figure out how to sample this process. So this thing was defined in the early 70s by Ferguson at Berkeley. And Gibbs sampling came around, about 10 years later, but then another 10 years before in the 90s, people started using Gibbs sampling for this thing. But in retrospect, it's actually quite obvious how to do this. By exchangeability, so if in Gibbs sampling, I'm looking at one data point, and I take it out and I hold everything else wixed. And I ask, what should I do with that data point now that everything else is held fixed? And by exchangeability, I can always move that to the end of the list and make it be the last data point. And so everything else has been fixed. So my Chinese restaurant process is run and run and run up to data point n minus 1. And now I ask, what does data point n do? Well, by the prior, they sit at all these tables, depending on how many people are at the table. All right? And then the likelihood says probably that data point of that table is just the Gaussian with that mean and covariance. Okay? So it's obvious how to sample. I just write those down as the prior and the likelihood and sample. And so if you do that, it sort of works, but it doesn't work very fast, and a lot of people have developed smarter versions of the samplers. So they exist. But anyway, that's not the point of this talk, so let me move on. I do want to make one other point about this. I guess this is an example. So here's a certain number of data points have arrived, and the mode of the posterior, i.e. the most probable number of components is 1, and there it is. And as more data points arrive, the mode of the posterior goes to 2. It looks like now 2 components are more supported by the data than any other number, and so on. And here's the number of components as a function of the number of data points. And as you can see, this is nonparametric. As I get more and more data, I start to see more and more structure and allow this to grow, but that grows slowly. My prior is log n, not as a function of n. But that's the mode. Of course, in this diagram here, they're all possible numbers of components have some probability, maybe vanishingly small. You can also do variational methods here. And this is really quite interesting. The Gibbs sampler is going to be very slow here. This is a hard, complicated problem. And in fact, it has a function of the dimension of a Gaussian mixture model problem. If you go up to 50, here's a standard Gibbs sampler. This is something called the TDP. It's I won't get into it, but it's a slightly fancy Gibbs sampler. There's also a CDP, which is even the sort of the fanciest possible Gibbs sampler that we know about right now. Is about this set of points right here. This is time in seconds to fit these models. And you can develop a variational method, and it's a standard variational method in the following sense. I have a complicated process, which is what I've been describing, that I can't do inference on exactly, and I write down a simplified process, and then I minimize KL divergence between these things as a function of free parameters in my simplified process. And that's what we call that's one form of variational inference. And what's interesting here is that the simplified process can be a finite dimensional process, but the complicated process doesn't have to be made into a finite dimensional process. It's still this infinite number of components are allowed kind of thing. And so a simpler thing to do would be just to truncate everything, to truncate the Chinese restaurant process and then work with a truncated distribution as your approximating distribution, and everything is now back in the finite dimensional world. And you can try that. It doesn't work as well as this. So in particular, this works well in the sense that it's fast. So there's the time. It's looking flat roughly as a function of dimension. It'll eventually will start to increase, but it hasn't in that problem up to 50. And then this is the held out log likelihood of the 2 Gibbs samplers as well as the variational method. And so normally you do a bit worse with variational methods than Gibbs sampling. We've run this Gibbs sampler until it has converged. There's no issue there. And the variational method is not worse. It is really just as good as the Gibbs sampler in this problem. So even this seems like it really requires Gibbs sampling. It's this complicated thing with all these, it's complicated prior and everything. You can develop a straightforward variational method that runs fast and is accurate. So. No, we're getting the whole posterior. Yep. It's a truncated stick breaking process. You're going to learn about stick breaking here in a minute, and maybe once I say that, you could ask again. There's a representation of the Chinese restaurant process in terms of something called a stick breaking process. That's an infinite sum. And if you truncate that sum, that gives us our Q distribution, our approximating distribution here. And the true posterior is not truncated. It's a full stick breaking expansion. Okay. Last little example. One of the things that motivated us to do this, actually, was an example in bioinformatics. I just want to mention it briefly, because I think it'll make more clear why we are going to this new set of ideas. One of the interesting problems that emerges in population genetics is to classify patterns of polymorphisms. So on the genome of each one of us, there are these sequences of C's, A's, G's, and T's, and we differ in a small number, a few million sites, individual sites. These are called single nucleotide polymorphisms. They're the main kind of polymorphism in the genome. And there only are two possible, at any given polymorphic site, there are almost always two possible values of the site. So C and T at that site, me and Paul may differ here. I have a C and he has a T, and then over here we can differ, and over here, and so on and so forth. So if there are K sites along the chromosome where we can differ, there could be up to 2 to the K different chromosomes out there in the world. Okay? And K is like 100,000 or something, so that's a huge number of possible chromosomes. And when you actually go out looking at people's chromosomes and see what you get maybe hundreds or thousands, not 2 to the huge number. So how come there are so few, even though recombination can mix all these things up and everything? So I think I've said that right here. So the word haplotype refers to the state of a single chromosome, and the problem then is to figure out what are the haplotypes out there in the population. And the technical difficulty is that you don't actually get to look at a single chromosome. If I go and grab some of your DNA, you've got 2 chromosomes, right? And on these 2 chromosomes, I'm going to have these alleles, and you lose the ordering when you actually do the assay. All right, so I might go along. Do I have one with 2 chromosomes on it? I think I want to go through this quickly. So here's a pair of chromosomes. We're diploid individuals, so we have a pair of chromosomes, and maybe I've got a TGA as my SNPs on one, and a CTA. Well, by doing the assay, I learned that at the first site have a C and a T, but I lost the ordering. I don't know which is which. All right, and so now you have something called phase ambiguity. You have to restore these phases. So I've lost the ordering. That's called the genotype. And you don't know which of these possibilities that are there. And if you think about that for about 5 minutes, you realize that's just a mixture model problem. Okay, the probability of a genotype, this set of pairs where you've lost the ordering, is just a sum over all the possible haplotypes of the probability of the haplotypes, which is given by population genetics, times the likelihood, which is that if you take those 2 haplotypes and you lose the ordering, you get that genotype. Okay, so it's just a sum over all those possible ways of getting that genotype. And that's just a mixture model. And let me skip over this slide too. I think. So there it is. There's this is known as the model for haplotype. And you have a probability of the haplotype times the probability of the genotype given the haplotype. And now the main problem here is how many haplotypes are there? So this is really the main part of the scientific problem. If we knew that, we'd know a lot about our human history. When did we have a bottleneck, and so on and so forth. So it's really the main problem. And now here's the motivating problem for why we want to do this thing called hierarchical Dirichlet processes. Suppose that I figure out how many haplotypes there are among a homogeneous population of, say, Africans. And they're like, it's thought it's sort of between 100 and, 10,000 is kind of a rough guess that people have, or, in a certain region of the chromosome. But now after I've done that with Africans, I'd like to do that also with Asians. And I'd like to also do that with Europeans and so on. And these people all share haplotypes because we all came from Africa originally. But how much sharing is there? Right? Which haplotypes do the Europeans have that the Asians don't have, and so on? And if you could learn about that, you'd learn a lot about the history of these populations at a very detailed level. So that's the problem we want to solve. We want to solve multiple clustering problems where we don't know the number of clusters, and we want to allow sharing among these clustering problems, and we don't want to build in the kind of sharing. Okay? So everybody got that. So that's a bioinformatics example, and then the LDA example gives you other examples. Okay, so now we'll get technical and try to solve this problem. Yeah. Yeah. Well, so we have a paper on this. You can look on my website about haplotype matching. Our method is a little bit better than the best method out there, which is Matthew Stevens' phase program. And ours is about 10 times slower than Matthew's program, and he had a head start too, so I think his will continue to be the one that's widely used. But it is I think a better method in some sense. But in particular, because you can build on and do other things like we're going to talk about now. Okay, so back to the Dirichlet distribution. Remember everybody what the Dirichlet distribution is? And so now let's generalize Dirichlet distributions to Dirichlet processes. So just like you take Gaussians and generalize them to Gaussian processes, or gammas and generalize them to gamma processes, and so on and so forth, let's now do that with the Dirichlet distribution. So the way you do this, and I'm going to now return kind of a circuitous route and motivate the Chinese restaurant process in a more fundamental way. So we did it kind of heuristically. Let's now be more fundamental. So I have some measure space here. That's the space we're on. I can put various measures on that space. And in particular, G0 is going to be some probability distribution on this space. So, this could be a Gaussian, for example. For concreteness, let's let G0 be just some, say a Gaussian on this space. And now I'm going to set up a notion of a measure on measure, or a distribution on distributions, all right, in the usual way you do with things like Gaussian processes or, by Kolmogorof's axioms. You partition up the space into K, or let's not use K, L partitions, L is 7 here. And you now look under G0 and see what measure G0 assigns to each of those regions, okay? So the Gaussian assigns to this region, 0.1, 0.2 here, 0.3 here, and so on. So I get L numbers that sum to 1. I guess I used capital K there. I shouldn't have done that. It's bad. Anyway, I get L numbers K numbers that sum to 1. Okay, and then I multiply those K numbers by a free parameter alpha naught to make them a scaling factor. And then I use those numbers as the parameters to a Dirichlet distribution. Remember, the Dirichlet distribution has these parameters, and these act like the mean. Okay, so if a particular G0 for a certain region is a big number, then with fairly high probability I'll sample from that region. Okay, so these numbers are like the mean, and then if I try to sample from the Dirichlet, I get these numbers now, which are random variables. And you think of them as kind of fuzzed up versions of those mean values. Like it's like on the simplex, you're kind of around those numbers. Okay, so that's what these numbers are. They're random variables around that. All right. And now you wave your magic Kolmogorov wand and you say, let's suppose I can do this now for arbitrary partitions. And let's suppose I can do it in a way such that I'm consistent among all possible choices of partitions. And the Dirichlet distribution now comes to help you because I can, for example, break this thing up into 2 subregions, and Dirichlet additivity allows me to have a consistency. Okay, if I break this thing up into 2, I'll get 2 new terms here, but the total Dirichlet probability will be the sum of the individual Dirichlet probabilities. Okay, so just like with Gaussians, you can get consistency among all possible partitions, and therefore, by Kolmogorov's axioms, there must exist a measure on measures. Okay, a probability distribution on probability distributions. Okay, so these are examples of that probability distribution, which is now a random probability distribution for specific regions. But I can now do it for arbitrary regions, therefore I must have a measure, and it's random, I must have a random measure. Okay, so that was set up in the early 70s, and it's an existence proof, but it's not very concrete. But let's kind of go with it for a minute, and now let's be Bayesian and try to do statistics with that kind of setup. So you say, look, I have an underlying measure, I have a scaling parameter, and fixed those, I can now generate a random measure on this space. So it's something like think of G0 as a Gaussian. This is kind of a fuzzed up Gaussian, if you will. Okay, now I repeatedly, from that thing, pick a parameter value. This is just a measure now on some space, and these are instances of that space. So I pick a phi1, that's just some point in the space, and then I get a data point from that. It's a parameter now for some data generating mechanism. Okay? And then I do it again. I get a new parameter, and then I get a new data point. Okay? And so that's called a Dirichlet process mixture model. Where this distribution on this now is not just some parametric form, it's non-parametric. It allows you, this can be any distribution in principle. All right, now, if G here were like the Gaussian, it were absolutely continuous, then the probability of any of these 2 phis being the same would be 0. All right, and that would be maybe okay for some applications, but for mixture modeling, that wouldn't be okay. That would say every data point is coming from a different cluster, has its own different mean and covariance, say. Right, we don't want that. And in fact, the Dirichlet process has the feature that this measure here, this random measure, is actually discrete with probability 1. So think of this as a set of spikes. All right, and therefore there's a certain probability that after phi1 has come, that phi2 is exactly one of the previous values of phi, or that previous value of phi. Okay. And in fact, so here's my setup. I get g out of this Dirichlet process, and then given g I get phi, and then given phi I get x. G is just a random variable coming out of some underlying process, and I can integrate over g. I can get that out of my problem. I can just get rid of that node. Okay? And now I can get a marginal distribution of all those phi values. And that marginal distribution is exactly the Chinese restaurant process. All right, so this requires some proof. It's not that easy to prove, but you can do it. So the conditional on these hyperparameters, and now in all the previous phis, the next phi has a distribution, which is, this is just the Chinese restaurant process written out mathematically. These are delta functions at all the previous phis. All right, so with probability given by a scaling factor, you land at exactly that same phi, i.e. you join that table. And with probability proportional alpha naught, you start up a new table. You get a new parameter value from that g naught. So it's kind of a bag of new parameters, and you either sit at one of the old parameters or you get a new parameter. Okay? All right, so the Chinese restaurant process emerges as a marginal distribution under the Dirichlet process where you integrate out g. Okay, now there's a third perspective on all these set of ideas, and it's called the stick-breaking construction due to Seth Rahman, and this took about 20 years to kind of write down and prove. So in 1994, Seth Rahman proved that under that existence theorem, it turns out there's actually a constructive definition, that G can be written with probability 1 as an infinite sum over random values bk, beta k, times delta functions at random values theta k. All right, what are these things? Well, theta k is just coming IID from G naught. So imagine just generating an infinite number of samples from G naught. And those are spikes now at positions in this space. All right, and then the weightings of those spikes will be random. Okay, and so if I do this again and again, I'll get different G's, which have different spiking positions and different heights of the spikes. All right, so now from this point of view, it's clear this thing is discrete, because by definition, really, it's discrete. Okay? And what are these betas? Well, they're called stick-breaking weights, and the way you get them is you take a stick of length 1, and then you break it at a position beta 1, which is given by a beta random variable with parameter 1 and alpha naught. So here's alpha naught coming into this picture. And so you get a length beta 1. And now you take the rest of the stick, and you do that again. You now break at a position beta 1 alpha naught, that's here, and you get a length beta 2, and so on. And you get all the betas doing that. And so it's clear the betas sum to 1. And so this is just really kind of a mixture model here over discrete atoms. All right, so if I do it once, I get a specific G, and that's what I've drawn here. If I do it again, I get a different G. And I keep doing it again, so I'm getting random measures, which are all discrete. And the choice of G naught kind of determines the shape of those random measures. And the alpha coefficient will determine sort of how roughly spiky I am, how close I follow the G naught or not. All right, so those are three perspectives on the same set of ideas, and they're all really useful. Some things are easy to show under one perspective, and some things are hard or easier to show on other perspectives. Okay, so going back to that picture now, you have a concrete idea of what this is all about. This G here is a discrete thing. All right, and so given that, these things, it's not surprising that you get clusterings. You get the same atoms being used over and over again. Depends on the values of the beta, which ones get used the most. Any questions about that? All right. All right, so now finally the setup of our problem, which is we want to do hierarchical versions of this now. Okay, because you now know how to do Bayesian mixture modeling with an uncertain number of components. That's what you've learned so far. But the whole setup here was that we had not just one clustering problem, we had multiple clustering problems, the Asians, the Africans, and so on. So the standard way Bayesian wants to handle any kind of multiple groups that are associated is to go hierarchical. So here's the standard Gaussian means problem. I've got these means, and then I've got data which are taken with Gaussian mean mu I. So imagine these are like cities, different cities, and these are heights of people in the city. And so I'd like to estimate the mean height of each city. All right? And the maximum likelihood solution is just to take mu hat as just the sample mean within a given city. But that doesn't tend to work very well from both a Bayesian and a frequentist point of view. What you really like to do is to shrink. You'd like to have the mu values kind of move towards each other. If this is a small sample, then this is going to be a highly variable estimate, and these samples over here are also people, and these are people, so somehow they should be related. And so I'd like to move this mu hat towards this data as well. And there'll be a little bias by doing that. People in this city might be taller than this overall, but I'll get a win on variance. So that's the frequentist argument for this. And the Bayesian is just sort of that, if I think these guys all have some similarities, let's capture it with an underlying variable. So I have a grand mean mu. Conditional on that, I get these are now random variables. I sample them, and there's my hierarchical model. And now if I do posterior inference under this model, the mu values, the posterior mean of the mu values will move towards each other, i.e. I'll get shrinkage. So that's just classical Bayesian hierarchical modeling, and there's the picture of it. All right. Now, how do we do that? That's the parametric world. How do we do that in the non-parametric world? It turns out it breaks. All right, so now we want to go to this multiple clustering problem setup. All right, so the first thought is just to do exactly what we just did. We have this original problem here. We had one of these, and now let's do multiple of them. We have now a Dirichlet process, Dirichlet process, Dirichlet process, and we link all these Dirichlet processes. These G, it's like the mu J's before, are all linked by underlying hyperparameter. Okay, so that's the first thing that we wrote down, and that fails completely, not just a little bit, it fails completely. And the reason is now is obvious once you think about it, which is that conditional on these two things, I now generate a GJ, my first G. That's a spiky distribution, and that gives me then clustering within a certain population. Now I do that again in my next population. I get a new GJ. With probability 1, none of those spikes will be in the same place as they were on the previous G. Okay, so I get no sharing of clusters among my groups. They're just like acting like mainly independent groups. They share a little bit by having the same hyperparameters, but that's really hardly anything. So you don't get anything like you'd like in classical parametric modeling. Okay, so how do you solve this problem? Well, you go to another level of the hierarchy, and it solves the problem. All right, so now what we do is we say that G naught is itself a random variable. It's a Dirichlet process. So this is now a random variable. It's coming from an underlying measure and an underlying scaling factor. So generatively, you fix those, and you now generate G naught. And we know with probability 1, it'll be a spiky distribution. Okay, and that's now the base measure for all these multiple G's underlyingly. All right, so we're passing into this guy as a base measure a spiky distribution. All right, and so it'll use those spikes, it'll reuse those spikes and sample from them, and it'll get a spiky kind of rearrangement. The spikes will have new heights, but they won't move the spikes because I got zero probability between the spikes. So all these G's will have the same positions of the spikes and just have different heights. All right, so we get sharing. The clusterings are all being shared among all these groups. Okay, so that's really, hopefully you understood all that. There's a lot of machinery you have to set up here, but the intuition is, and the idea at the end is really pretty simple. So there's kind of a pictorial version of that. You now, first of all, sample from G naught, you get a spiky thing, and then those serve as the base measures, and you get kind of diversified versions of those base measures. And I'm kind of starting to get near the end. Let me, now we've now defined a new mathematical object, the hierarchical Dirichlet process. The Dirichlet process where the base measure is itself a Dirichlet process. So the standard notion of, Bayesian notion of a hierarchy. And you can now give characterizations of it as a stick-breaking process and in terms of Chinese restaurant ideas. And let me now kind of skip a little bit of this so I can kind of get to the last point. The analog of the Chinese restaurant process is what my colleague Whye deemed a Chinese restaurant franchise, which is now I have multiple restaurants. And here's a customer coming in. They sit at a certain table at a certain probability. And then at that table, they can choose from a number of dishes, which are shared among all the restaurants in the franchise. And these dishes become more and more popular as more people choose those dishes. And so it's the same Chinese restaurant idea, but now extended to 2 levels. And Whye has actually written a Gibbs sampler for this for arbitrary hierarchy. Okay, so I've been talking about 2 levels of a hierarchy throughout, but the software is actually, Whye has done a very nice job of writing an arbitrary hierarchical Dirichlet process up to an infinite number of levels. Okay, so now we can return to, we have this tool in our hands to solving some problems with this. And so the first one to point out is just now we can do the LDA problem in a clean way. So how many topics in LDA? Well, now I don't have to decide that a priori. Okay? So my first document comes in, I start looking at the words one after another. This is kind of conceptually what a Gibbs sample would do. It looks at the first word. It says, does that belong in a cluster? Well, yes, I'm the first one. I have to start a cluster. Next word comes in. Do I belong in that same old cluster, or should I start a new cluster? And so on. I've gone through that entire document. I've now generated a certain number of clusters. All right? And now I bring in my new document. And the dumb thing to do would be just to make a big, long document out of everything. Okay? And not respect the fact there are different actual document structures. So you don't do that. It's this Chinese restaurant thing. You now have the dishes have now been kind of allocated. And you bring the next document in, and now new tables get allocated with new dishes. And you actually respect the notion that there are documents. So anyway, we can now solve the, so there's really no reason to do LDA assuming you know the number of topics, unless you really think you do know the number of topics. Okay? And here's an example. I think I had a better example. I think, let me see. If I was too lazy to turn these slides into PowerPoint, and I still have them in Ghost View. Yes, here we go. Let me show you this application. Full screen. So we applied this to a corpus which is familiar to some of you. The NIPS conference has all of its documents or all of its articles online for like 11 years. And so we took all these articles and did our LDA style model of them. And these articles are divided into sub-areas: algorithms and architectures, applications, vision, and so on. And so we use an HGP now to find clusters in each of the sub-areas and share them among sub-areas. And so you can compare several models. One of them is that you just have a separate hierarchical Dirichlet process for each of these sections, algorithms and vision and so on. And there's no sharing, so that's one model. Another thing is to ignore the distinction between the sections altogether, just lump everything together, and that's another model. And then here's the third one is the smart one. And it's worth noting that this already has 3 levels of the hierarchy, all right, because there are words and then there are documents. And already at that level, there's multiple documents within a section. You're using the hierarchy of LDA. And then, but we have no multiple sections, so we have another level of the hierarchy. And here's some examples of doing that. This is the number of vision training documents. So you start from 0 and you add more and more documents. And the flat model, which just lumps together everything, starts out pretty well because it's got a lot of data available to it, but it sort of only slowly goes down in perplexity. The smart model starts a little tiny bit higher, but it quickly picks up on this extra structure and exploits the previous clusterings that it's had from the other documents. And it does the best. And if you have the independent model, well, it does much, much worse for small amounts of data, and eventually you get enough vision documents that you start to do okay on the vision documents anyway. So this thing approaches it. And this is an interesting plot where you previously train on one other area, not on all the other areas, which we're doing over there. You previously train on the learning theory area, or the applications area, or the algorithms and architectures area. And then you see now how much perplexity you get in the vision area. And you can sort of see here that the most gain is gotten by pre-training on the applications papers, and then less gain on the algorithms papers, and then even less gain on the theory papers.
So now, if I have the prior information, for instance, no conference can have more than 5 conferences.
Yeah.
And how could that have a prior information?
Well, you can put it easily into the sampler. It's a kind of implicit use of the prior. You can put it in there. You've defined, the object you define mathematically is complicated, but you can put it in the sampler. Okay, so that was, and so I guess that was some shared topics among the things. Let me not get into that. And let's see, how do I do this? No, damn you. Okay. I think I'm going to skip over those. I'm about to finish. So there's lots of other applications of this. That was to the LDA model. Here's another application. Suppose you're trying to do hidden Markov modeling and you don't know the number of states, which is most hidden Markov model applications. You don't know the number of states. What do people do? They guess. Or they try a couple and they do BIEC scores. Not very impressive science. So what if you want to have this be uncertain and you want to infer the number of states? Well, this is you can't just do a standard Dirichlet process, because conditional on the current state. So I'm at some current state and I'm trying to decide which next state to jump to. I don't know how many next states there should be. So it's the Chinese restaurant process. I'm sitting there I look at all those next states like I jump to, and I decide to jump to them with certain probability, but I decide to start a new state with some probability. Now, once I've done that from this current state, I want all the other current states to share. I want them to also be able to jump to that new state. So it's exactly this group data problem where the groups are defined by the current states. Okay? So it's exactly the problem, and so this HDP approach allows you to do a very clean version of a HMM with an uncertain number of states. And so the software just goes right over, you can do this. There was a previous paper at NIPS on something called the infinite HMM, which was roughly this same idea, but it didn't get the inference algorithm right. And the reason was because they kind of confused, they had a notion of a hierarchical Dirichlet process, which is the Chinese restaurant process. And you have to go to this franchise picture, and that comes out of going this whole long route through the Dirichlet process, underlying measure theoretic machinery, the stick breaking and all that. So anyway, I hope you didn't mind going through all that stuff, but the point is that when you do that, you can work on more complicated applications like this, and it works out easy and correctly. So there is software available for this if any of you are interested. And then finally, here's an application of modeling topic hierarchies. So this is a now very different use of the word hierarchy. My computer science colleagues always get confused. And we originally submitted this paper on hierarchical Dirichlet process, which I'm very pleased by, and it was rejected at the ICML conference, which is not even a very good conference because they thought that this is just two levels of a hierarchy. How could that be interesting? And of course, they're confused about Yahoo-style hierarchies, where you want to have very deep hierarchies, and Bayesian hierarchies, where you want something that was fixed before to be random. So you guys wouldn't be confused about that, but a lot of people are. But suppose you want to use these kind of ideas to model Yahoo-style hierarchies. So at every node of a Yahoo-style hierarchy, you want to have a Dirichlet process, and you want to link these Dirichlet processes. So now you've got to go to the Bayesian other kind of hierarchy to do that. All right? And so let me sort of skip over this. We had a paper on something called the nested Chinese restaurant process, which is just exactly that. I have a Chinese restaurant process at every node of a Yahoo hierarchy, and I want to share information among them. And at the end of the day, instead of a person coming into a restaurant and sitting at a table, they do a whole path. They come in here, and they choose a branch to go out. And then come in here, they choose a branch to go out. And they can always start a new branch. Okay, so it's the same kind of metaphor, but done in the notion of a computer science style hierarchy. And we did this on a number of different hierarchies. Dave Blei got the entire JACM sets of abstracts and ran this thing. And here's the posterior mode that comes out of this. So it likes the words the, of, and is an and at the top. That's good. It found the function words and put them at the top. Because every time a person, you generate a new document, you go down a certain branch. And so those words are used by everybody. And so you ought to put the function words at the top, and it does. And then, you pick this branch, you're now doing programs, language, rule resolution systems, and then looks like some semantic situation calculus kind of stuff. And then over here, it looks like it's more sort of networking and so on. All right, so that's really nice. That is the posterior mode tree. The number of branches here was decided by Bayesian calculus. No heuristics, no nothing, no model selection explicitly, and the number of everything was done. There was just this gamma alpha hyperparameter to set, but nothing else. And I'm done now. So there are a lot of papers on this. We've been doing this for a few years now, and there's a long paper called Hierarchical Dirichlet Processes. If you want to see kind of a paper that has the different perspectives, the stick breaking, the blah blah blah, kind of in one paper, that one does it. And there are various other papers on these applications. And there is a conference on nonparametric Bayesian statistics that's held every couple of years, a workshop. And you can type in nonparametric Bayesian into Google, you'll find that workshop. And I encourage you to do that. There's lots of really interesting work being done in that field. We've been talking about Dirichlet process today. Those are 30 years old, right? And there's lots of other processes, like neutral to the right processes and gamma processes, beta processes, and so on and so forth, which are this whole spectrum of things that one can use, and hopefully creative ways more computationally. So anyway, you don't have, we all want to be nonparametric, and you can still be Bayesian and be nonparametric. Kind of the main message of the talk. So thank you. John. Yeah. Yeah. sort of seconds to minutes. Minutes. Yeah. Yeah. So this is not just Gibbs sampling, it's fancier Gibbs sampling. And there's a good paper that Radford Neal wrote on various algorithms. He kind of got into this at some point, and he had like 9 algorithms for doing just basic Dirichlet processes. And all of those you can extend to the hierarchical Dirichlet process framework. And roughly speaking, you don't want to do Gibbs sampling because that kind of moves one data point at a time. It's kind of hard to pull it out of a cluster and put it into another cluster. So you want to do split and merge kind of things or other sort of more metropolis hasting kind of things, but you do something bigger all at once. And so anyway, a lot of people have worked on that. I'd say there's not so much left to do there per se. Well, that's not quite true. There are some things you can still do. Certainly non-conjugate things within the sampling framework is still kind of challenging. But I'm going to work on the variational thing, because that way we have one paper on that right now, and it really worked extremely well on just old-fashioned Dirichlet processes. And so I'd encourage people to think about that, not just the KL-style variational, but the belief propagation, data, free energy kind of variational things as well. How can they be done here? I mean, then we'd be really making a very interesting contribution back to Bayesian statistics. So that took like less than seconds to fit the Dirichlet process mixture up to 50 dimensions of Gaussian Gaussian mixture models. And if you're going to do BIC scores, et cetera, you're going to look at all K, and you're going to calculate your score, and you're going to fit inside of the loop and everything. You're going to do the same amount of work. Yeah. Well, so the literature, the best thing that people have done in the literature is to put a diffuse gamma on it and integrate over that gamma. You can do that analytically. The Dirichlet process, even though it's a process, has a Dirichlet at its core. And the conjugacy of the gamma and the Dirichlet come in, and you can integrate over that. In our software, what we've been doing is we've been integrating over that analytically. That one has really not been an issue. You set that to whatever, 1, anything. You try different values, and it doesn't change your results at all. But if you work with just alpha itself, and you set it to 1, you get one answer. If you set it to 10,000, you get a different answer. But not even on all problems. This is a kind of a log-n tail, and setting it to 10,000 just makes that tail go further and further out, more like Zipf's law, right? If you set it to 100,000, you'll kind of get Zipf's law. And if you set it to 1, you get something that's a little too sharp. But if you have not so much data, setting it to 1 is not so unreasonable. You're not going to see Zipf's law if you don't have so much data. And so, 1 is not so bad. But I should say we don't ever just set it to 1, at least in most of the real work we publish. We either do the gamma or we just use marginal likelihood and maximal empirical base. We just do that. But, a lot of people work on this, and a lot of people worry about that. And, if you're going to publish a paper on this, you probably should try different values, because indeed it tells you how likely you are to set up a new cluster. But in the prior, of course, the data comes in, and it might tell you there's like 5 clusters, and so the prior doesn't matter so much. But, yeah.
Super intuition about how to compute this without doing anything fancy. Let's say I want to produce a correlate to get to it. You kind of simulate the Chinese restaurant process, by observing data, and then you kind of have.
So this is 2 lines of MATLAB. Let me tell you what these 2 lines of MATLAB had. All this math you can forget. Yeah. Yeah. Well, it's on the website. No, so I'm going to give a tutorial on this stuff at NIPS this year. All right, and I'm going to do my best to make it easy, because I think if a lot of people would see how easy it is, they'd start to use it, and we'd learn a lot. So here are basically the 2 lines of MATLAB, which is that you take your endpoints, and let's suppose that they're in some clustering right now. Okay, they're sitting in all these various tables, right? And we're doing Gaussian mixtures just for concreteness. Okay, so now I go and I take point number I, okay, and I pull it out of that table, off of that table. All right, and now what I do is by changeability, I think of it as the last point to arrive. So all the tables have been occupied; they're all sitting there, and I say, what's the probability I'm going to now join each one of these tables? Right, by the prior. It's a proportion of the number of people at the table, all right? And then there's the prior on all the thetas, all right? Either I integrate them out, that's the usual way of doing it, or if I have the thetas being represented too, I just index into that theta, okay? And so I'm a data point. I pulled myself out of that table. I say, what's the probability under a prior that I'll sit at each table, and what's the probability given the theta at that table that I came from that table? That's the likelihood term. That's just a Gaussian. So I multiply that Gaussian by that prior, that count, I normalize, and I then go sit at another table under that probability. Or I create a new table. right? And then there's just the data structures underlying that handle, data points being indexed into different tables. But that's it. Those are
And then the mode is run for a long, long time.
Run for a long, long time. And
one
the number, you count the frequency of the number of tables. For each table, the number of points that are there, right? Or the number of occupied tables, right? At some point in this sampling process, 5 tables are occupied,
right.
And then 7, and then 3, and so on. I just take the mode of that. So that's just under the prior. There's a probability. There's a theta distribution. So that gives me, by integrating out theta, the probability on all x's. It's not a specific theta now, it's overall possible thetas. Yeah, it's really easy. And there's really no reason to if you're going to do anything at all fancy with any other model, to just add this kind of layer in there. With what?
With online learning, this is sort of what they do.
Well, yeah, depending on what you mean by online learning. You're right. I mean, here we're using this exchangeability kind of ideas, and we're getting something that really has a posterior distribution and so on. So, that's a certain goal. If you're being Bayesian, that's what you want. Online learning is kind of, has frequentist goals generally. You want to prove things about it. And then the algorithms themselves, yes, they're a kind of add one thing kind of thing. But, Gibbs sampling is a little different. It looks at all future points as well as all past points, right? Yeah.
But I use these frameworks to think about Gibbs.
To think about? Let me try to answer a slightly broader version. I think that all this work on, on graphs, and the probability distributions on graphs is definitely closely related to this. Just thinking about this Chinese restaurant, this is a prior, and and some people are aware of connections. Works on. He has a long history in his restaurant process, and he works on this network probability problem. And the geneticists have worked on a lot of these ideas for a long time too. The Chinese restaurant process is called by Whye sampling formula. And they've worried about how many species are on certain islands, kind of things, and how much activity, and so on. There's a lot of modeling, coalescent processes and stuff. So if you're into that world of trying to, make good distributions that generate reasonable internet-looking kind of things, I've sort of followed that for up until a year or two ago, and I don't know what the latest kind of is, but they're in this spirit. I don't think it's the Dirichlet process per se, but I think that fancier versions of these. The Dirichlet process can be generalized in a whole lot of interesting ways. So remember it was beta of 1 comma alpha. Instead of that being a 1, make that another parameter. That's a very natural generalization. You get what are called the Pittman-Yor processes. And all these things have different properties. And if you start putting them into graphs, they'll generate different kind of distributions on graphs. So I don't work on this, so I don't know the answer, but I know there's lots of interesting connections. Was that answering something close to what your question was about?
I expected you to say.
Well, so, the statistics in this talk was just kind of you add a likelihood and then you try to, arrange the sampling correctly. The probability theory behind this was the more deep stuff, and that's the classical contributions. And people doing network, probability distributions on networks those are probabilists. Those guys have a lot of these connections already kind of in their sights. Yeah.
Does the Chinese restaurant process have a bias to creating larger clusters?
Yeah, it has a bias. It's a good question. It has a log n bias on the number of clusters, and that may be good or bad depending on your problem. But it also tends to like to have this rich get richer. It likes to have one big cluster. And that may or may not be appropriate for your problem. So there are other versions of these processes which don't have that property. And you're free to think about these things at any number of different levels. You can try to set up a new kind of process, not the Dirichlet process, but the beta or the whatever process. Or you can think about the Chinese restaurant. Say, I don't like that rule of assigning people to tables. I want you not to go to the table to the most number of people. I want you to go to the table to the least number of people. And now if I can prove exchangeability, I've got a perfectly well-defined process that I can give sample from. And I don't have to worry about whether there's an underlying measure theoretic definition behind it. Or you can go to the stick breaking thing. You don't have to break sticks in that way. That leads to these one big stick and then smaller sticks. I'd like to break sticks in a different way. You can do that too. In fact, the TDP thing, I went really quickly over the Gibbs sampling. There were 2 different Gibbs samplers. TDP explicitly represents the stick, and it keeps those beta values around. And you can do that in a different way. You can keep your beta, you can sample from another distribution and keep them explicitly around your Gibbs sampler. Okay.